Welcome to part 4 of Matrix Algebra 101, part of the TLR course. Part 4 is a very important part because we will get closer to the real reason why we're using matrix algebra and the role that the inverse plays in this in calculating unknowns, where we have a same number of unknowns as the number of equations needed to enable us to calculate the real value of, or the values of these unknowns. We then just kick off by talking about the inverse of a matrix, and this is very important as we need the inverse to assist us in calculating the number of unknowns that will be needed um, or is needed to get the real the value of these unknowns. So we have to define the inverse of a matrix, and this is basically how the definition works. Suppose we have a matrix A, capital A, and it's an n by n matrix. So the first thing we see here is that it must be a square matrix. Only a square matrix can have an inverse. So the inverse of A would be another matrix exactly of the same dimension or order, and we write it as A superscript minus 1. So A superscript minus 1 indicates the inverse of matrix A. Now, and this is very important. The definition of the inverse of a matrix is basically a new matrix that when multiplied by the original matrix gives us a new matrix, a new square matrix of the same order, but it's an identity matrix. So you know what an identity matrix is by now. It's basically a square matrix with ones on the diagonal and zeros on the off diagonal. So that equals, in normal algebra, that would be equal to the number 1. So again, an inverse of a matrix is defined by a new matrix of the same order if multiplied by our original matrix gives us an identity matrix of the same order. So you can also pre or post multiply with the inverse matrix. It doesn't matter. So if we have a matrix A, in this case a 2 by 2 matrix, 2 rows, 2 columns, 2, 1, 3, and 4 are the 4 elements. Its inverse is this matrix. So when we multiply it by the inverse, it gives us again a 2 by 2 matrix and identity matrix. And you will see that it doesn't matter whether you pre or post multiply with the inverse matrix, it will give you the same answer. It will not be expected from you to know exactly how you calculate the inverse, but you must be able to do it using other means such as a spreadsheet or another program to enable you to do that. So you must be able to calculate an inverse, but the rules and how that is done is not needed for this course. It's basically a tool that you will be using in future. So again, the inverse of a matrix, it doesn't make sense. It's elements, but if you multiply that with the original matrix, it will give you an identity matrix of the same order. A very important part is that there is not always an inverse. Remember, only a square matrix can have an inverse, but it's not guaranteed that a square matrix will have an inverse always have an inverse. So there's 2 ways that one can determine whether it's possible to calculate an inverse of a matrix. The first one is to determine its rank. Remember when we did the rank of a matrix? So a matrix have to be of full rank. So there should never be any dependency of any row or column with another row or column. When we handled the linear dependency, we we basically pointed out, or I pointed out, that you have a linear dependency if any row or any column is dependent on any row or any rows or columns uh, of the matrix, of a matrix. So a matrix needs to be of full rank, otherwise you will not be able to calculate an inverse. The other way, or the more easier way to do, is to compute its determinant. So when the determinant of a square matrix equals 0, the inverse will not exist. So a way to test, if you have, let's say, a 5 by 5 matrix, and you want to know whether it's possible to calculate an inverse for that 5 by 5 matrix, you could first then just calculate the determinant. If the determinant does not equal 0, it means that the matrix is a full rank and an inverse is possible to calculate for that matrix. If a square matrix has an inverse, it's said to be non-singular, or it's invertible. So it's possible to calculate the inverse. But if a matrix is singular, you cannot calculate an inverse for that matrix. So any singular matrix, if any row or any column is dependent on any other rows or columns, or a factor multiplied by those rows or columns, it will be a singular matrix. It will not be a full rank, and you will not be able to calculate the inverse. In this course, it's not expected of you to calculate an inverse of a matrix by hand or to know exactly how to do it, but it is expected of you to use another means to calculate an inverse, such as a spreadsheet or any other program that can calculate an inverse for you. Good. That brings us at the real reason why we looked into matrix algebra in the first place, and that is to calculate unknowns where we have a number of equations. So if we have a number of equations, in this case you will see you have all these equations where you have x1, x2, x3 and so on as unknowns, or it could be a, b, c and d and so forth, equals to a specific number, like the example we used in the very first part, and you have an equal number of linear equations compared to the number of unknowns, and you would like to know what these values, what's the value of x1, what's the value of x2 and so forth. So each of these x's then is an unknown value, and the a's would be what we call a coefficient. So this could be, let's say, 5x plus 3x1 plus 3x2 plus 7x3 and so on equals 23. This could be, say, 7x1 plus or minus 4x2 plus 23x3 equals 433 and so forth. So these are the coefficients. A would then be called a coefficient, and obviously x1, x2, x3 would be our unknown value. And then y is the known quantity. We also talk about the right-hand side of the equal sign. So we could then also rewrite all these equations in a new manner. We have a coefficient matrix A, and A will be a square matrix with the number of unknowns as the row and the number of equations as the column. So that would be the order or rank of A, multiplied by our a column vector of our unknowns, x1 to x, how many we have, equals a column vector of our right hand side, or the known quantity in the equation. So basically this is just a rewrite in matrix notation of exactly the linear equations here at the top of this slide. So like I said, it's actually written down here. X is an n by 1 column vector, one column, number of rows, number of unknowns. A is an n by n matrix, so number of rows, number of columns, the number of equations, and the number of unknowns. And Y is then a column vector, also the number of rows or the number of equations, and it's obviously a column vector, so you only have one column. So if we have now seen, we've rewritten these equations and unknowns in a matrix form or matrix notation. That A is our matrix with the same number of columns as the number of unknowns and the number of equations, so it's a square matrix. We also call that the coefficient matrix. We have X as a column vector of unknowns, so you basically have x1 to x how many unknowns there are, or equations, and Y then our so-called right hand side, which is a column vector with the numerical values on the right hand side of the equal sign. So the first step would then be to pre-multiply by both sides with the of the equation Y with the inverse of A. So obviously we have to first calculate the inverse of A, and then pre-multiply both sides with the inverse of A. So basically then A minus 1, we also talk about A minus 1 or the inverse of A, pre-multiplied by that, and the same on the right hand side. And since we know that A minus 1 times A gives us an identity matrix, and any number multiplied by an identity matrix or another matrix multiplied by an identity matrix just give us the original matrix, we know that that part here, A minus 1 times A, falls away, and we end up with X, that's a column vector of unknowns, equals the inverse of A multiplied by the right hand sides. So basically, practically, this means we have to determine the inverse of A and multiply the inverse of A with our column vector on the right hand side. It's possible because the number of columns in A equals the number of rows in or A minus 1 equals the number of rows in Y. So we are allowed to multiply those two matrices, the square matrix with the column vector, which is the inner column matrix. So as long as we can calculate A minus 1 or the inverse of A, we can solve X. So we will end up with a vector or a solution for each of these unknown values. So we'll end up with a column where x1, the first unknown, will be the top element, x2 will be the second element, and so forth in our column vector. So let's use this as an example. Here we have three equations: x1 plus 2x2 plus 2x3 equals 1, 2x1 plus 2x2 plus 2x3 equals 2, and the last equation and with our three unknowns, 2x1 plus 2x2 plus x3 equals 3. So basically those are our three unknowns, x1, x2, x3, and three equations. We can rewrite this in matrix notation. This is our coefficient matrix, A in this case, 1, 1x, 2, 2x, 1, and 2, 2x1. So that's our that's our first column. Or if you look across, if you want to look at the equation itself, the first equation, 1, 2, 2, 1x, 2x2, and 2x3. And the same then the coefficients on our second equation and our coefficients in our third equation. So 3 unknowns, 3 equations, that gives us a 3 by 3 matrix, the coefficient matrix. Our 3 unknowns, x1, x2, x3, that's a column vector, the 3 unknowns. And then our right hand side with our 3 numerical values gives us a column vector on the right hand side of the equal sign. So here we've basically set up our 3 by 3 matrix. We've set up the column vector of unknowns, and we have set up the column vector of the right hand side. So now we basically pre-multiply with a minus 1, or the inverse of our coefficient matrix. There's the inverse of our coefficient matrix. We pre-multiply it with our A matrix. That will give us an identity matrix, which is then, if that's multiplied by our column vector, just sort of the column vector remains. And we also do it on the right hand side, pre-multiplication of the a minus 1, or the inverse of our coefficient matrix, with our right hand side column vector. And that means that we end up with the unknowns on the left hand side as a column vector equals to the inverse of our coefficient matrix times our column vector at the right hand side. And that, if we then do this calculation, multiplication on this side, on the right hand side, we end up with a column vector which basically gives us the answers to our what x1, x2 and x3, what the values of x1 and x2 and x3 is. So basically the first element there will be x1, second element x2, and the third element in this column vector would be x3. So x1 equals 1, x2 equals 1, and x3 equals minus 1. So that gave us the solution to our 3 unknowns. And that's the way matrix algebra assists us in solving cases where we have an equal number of unknowns and an equal number of equations, linear equations. Obviously, if there's linear dependency, if any of these rows are dependent on any of these columns, it means that that matrix is not of full rank, and it also means that we will not be able to calculate an inverse for that matrix, and then it's not solvable in that case. So in any of our equations, if there are linear dependencies, not be possible to solve these unknowns with the number of equations. Here's a second example, exactly the same type of example as the first one, maybe a little bit more simpler, where we have 2 unknowns, x1, x2, and 2 equations. So our first equation then say 3x1 plus x2 equals 3, and our second equation say 9x1 plus 4x2 equals 6. And we would like to know what x1 and x2 is, the unknowns. So our coefficient matrix then, two equations, 2 unknowns. So our coefficient matrix is a 2 by 2, and let's call it A again. And you will see the coefficients 3 and 1, 3 and 1, and 9 and 4 would then form the elements of our square matrix, coefficient matrix. We have 2 unknowns, x1, x2, so we have a column vector, x1 and x2, and let's call that column vector small x. And then on the right hand side of our equations, 3 and 6 is then a column vector 3 and 6, and let's call that column vector small y. So this is setting up our coefficient matrix, a two column vectors, column vector of unknowns, and a column vector of on the right for the right hand sides of all our values of the equations. So obviously we then need to get the inverse of A and multiply. So our left hand side then would be our column vector of x1 and x2, basically our column vector of unknowns. On the right hand side then we have the inverse of our coefficient matrix multiplied by the right hand side of our equations, and we end up with the answer of our unknowns 2 and minus 3. So x1 will be 2 and x2 will be minus 3. Again, you need to make sure that there is an inverse for the coefficient matrix, and you have to calculate the inverse up front of the coefficient matrix and then multiply it out with your right hand side column vector, and that will then result in giving you the answers for your or the resolutions of your unknowns. So this can then be used very widely in terms of statistics, and that's basically what's being used in statistics and obviously also in animal breeding. So other uses would be the calculation of the sums of squares or sum of squares, and we will be using those examples later on in the course. It's also being used for variance and covariance calculations, and to set up a variance and covariance matrix. So what is the relationship between a set of variables with another set of variables? If I select for one trait in cattle or sheep or pigs, what will happen to the genetic values of the other traits? So this is then basically being used very widely in statistics. Just to recap a little bit on some of the what we've handled in this part of the course. So we usually, in terms of matrix algebra, we use capital letters to indicate matrices. Capital A, B, and C would be then matrices. A or a superscript little stripe will be the transpose, and you know what a transpose is. That is where the rows becomes the columns and the columns becomes the rows of a matrix. A superscript minus 1 or minus 1 superscript denotes the inverse of a matrix, and remember the inverse of a matrix, if it's calculated with the matrix itself or multiplied by with the matrix itself, it ends up with an identity matrix of the same order and rank. I is such an identity matrix with the obviously a number of columns and rows. It's a square matrix. If it's small letter, usually when it's a small letter, it's a real number or a scalar. Numbers as we know it. Here are some transposition rules. You can read through that. So the transpose of A, transpose will be A. That's obviously. So the transpose of A is where the columns of A becomes the rows, and the vice versa. And if you have the transpose of that, you end up with A again. A plus B's transpose is the same as the transpose of each of these matrices. A times B, or when you multiply A with B, the transpose of that will be equal to the transpose of each of them. And the same where you have three matrices multiplied, the transpose of them will be the transpose of, but you will see in reverse order of those. We have done addition and multiplication. I'm not going to go through that again. You can go back to previous parts of this course to just look at that again. And then also multiplication of a scalar with a matrix. Inverse rule, A times its identity or the identity matrix of the same order gives you A. If you multiply A with its inverse or the inverse of A with A, you end up with an identity matrix of the same order. And this also means that the inverse of the inverse will bring you back to the original matrix. I'm not going to go through the other three here. That is maybe of lesser importance. So it's also then some of the notations that's important in matrix algebra. Vectors, usually boldface or lowercase letters refer to vectors. So we have set A or X refer to vectors, A and X respectively. A or subscripts usually refers to the elements of the matrix, where the first letter of that subscript would be the row and the second one J, so that gives you the exact location of that specific element. Then generally in terms of matrices, we usually use capitals and boldface. And then the dimensions of the matrix is usually also a subscript, let's say an I and a J in this case, which refers to I by J matrix, the number of rows and the number of columns. So let's say it's a 6 by 6, it will be A66 will then denotes an order of a matrix with an order of 6 or size of 6. A transpose is denoted as this, with a little stripe as a superscript that denotes a transpose of A. I, we have mentioned in the identity matrix, and then an I with a little subscript will denote the size or the order of a identity matrix. So as I with the little 6 at the bottom means a 6 by 6 matrix. 1 refers to the sum vector, a column vector, and all its elements equal to 1. So IN will be a column vector with, let's say, if that's a 20, it's a column vector with 20 rows in it or 20 columns in it. The determinant of a matrix is written. You have the matrix capital bold and with two parallel lines on side of that, and then X refers to a matrix of deviation scores derived from the raw scores of a matrix X. We haven't dealt with that, so that is also not important. You needn't memorize that as well. Very important for the next part, we will be dealing with some examples that you have to do yourself, and it's very important that you familiarize yourself on how to use your computer or the internet to assist you in the calculations needed in matrix algebra. Here are some examples of places where you can go and look on the internet in terms of using different means to calculate these things. Thank you very much. This was then part 4, and the last part of matrix algebra 101 will then follow on this.